All right. Good morning, folks. Happy Monday. Um, so we're going to go ahead and get started. I do want to start by talking over this week's announcements on Canvas. I'm going to share that screen first. All right. So yesterday I posted this announcement in case you haven't had a chance to take a look at it yet. But yes, believe it or not, we are in our final week of summer school. So first off, hats off to you for choosing to do such an intensive course over the summer, and also doing it under these situations where you know you're not going to get an in-person learning experience. But I hope that it's been a rewarding experience for you all. I know it hasn't been easy, but I've seen a lot of incredible transformations over the course of this summer session from you guys. So anyway, for week 8, we're going to be covering 11.5 today. Tomorrow, we're going to take a look at 11.6, and then on Wednesday, we'll take a look at 11.7. Okay. We have a bunch of quizzes due this week, even though it's our last week. So on Wednesday, we'll have quiz 14 due, which is going to cover 11.5 and 11.6, okay? So that's going to be due at our regular time, 9:30 on Wednesday morning. Quiz 15 is due on Friday morning at 9:30, and that covers a section 11.7, okay? There is going to be an optional quiz 16. It is optional. You do not have to do this. It is an opportunity if you have a low quiz grade, you can use this quiz 16 to replace your lowest quiz grade. This is also due by 9:30 on Friday morning, okay? And then a last announcement is that the final exam is going to open at 9:30 on Thursday morning, and it will close at 9:30 on Friday morning. So you've got 3 big last assignments that are all due Friday morning by 9:30. So if you have not done so here, I did include a link where you can find the list of topics that will be covered on the final exam, as well as point values for each section, okay? I know it's not something I've been doing for the regular exams, but I figure for the final, it's been such a long summer. It is a very intensive course, and I do want to steer you in the right studying directions for the final exam, okay? Are there any questions about the announcements before we get started?
Yeah, could the final still replace one of your lowest exam grades or not?
Yes, so Carl asked if the final exam will follow the same structure as the last 2 exams, and that is correct. So within the 24-hour window, make sure that you have 4 hours to sit and take that.
Thank you.
All right, any other questions? You're welcome. All right. Well, if there are no other questions, then I'm going to stop sharing this screen. And so unless you've somehow lost the privilege to have your final replace your lowest grade, then yes, you still have that. The final can replace your lowest test grade. Okay. All right, so we're in section 11.5 today, which I noticed that a bunch of you are already in the blank notes. So I'm going to go ahead and share my screen for that. All right. Okay, so let's take a look at section 11.5, okay? It covers a topic called absolute convergence, all right? So let's start with what we know. Things that we know that there are sequences and we know that there are series. And we know that convergence and divergence mean different things for a sequence versus a series. But the big question that we've been asking ourselves over the last week is whether a series is convergent or divergent. And we've had a whole bunch of tests that we've learned to help us determine whether something is convergent or divergent. What are one of the tests that we've learned for convergence or divergence?
Integral test.
Yeah, we've got a basic comparison test. Exactly. Basic comparison.
Integral test.
Limit comparison. Integral test. What else? I think we had one more.
Divergent test.
Yeah, we had the divergence test. Okay. So these were a few of the tests that we had learned, and each one operated in a different way. And so that was one of the things I was really looking for on the exam last week, was making sure that we knew how to sort of explain our reasoning, like knowing, okay, if this happens, then I know it converges because of this. Or if this happens, I know that it diverges because of that, okay? Now, in terms of what's new, okay, we're going to introduce a new type of convergence, and we're going to learn two more tests, okay? Now, before you freak out, I actually think that these tests are maybe a little bit easier than the integral test or the basic comparison test. So if you were someone who really liked the limit comparison test, then the ratio and the root test, I think, will be right up your alley, okay? So there is something called absolute convergence, okay? And what we've been studying so far has actually just been what we call conditional convergence. All right, so conditional convergence is what we've explored so far. And what we're going to learn about today is something called absolute convergence. And so now, instead of saying, does it converge or diverge, we're really saying, is it an absolute convergence, conditional convergence, or divergence? Okay. Now, to help us out to determine those two, we're going to take a look at the ratio test and the root test. Okay, so let's get started with our absolute convergence. So for absolute convergence, we're going to define that an infinite series of this absolute value of a sub n, okay, is going to be equal to a sub 1 plus a sub 2 plus a sub n, all the way until you get to the end, all right? So along the way, we're just going to be taking the absolute value of each term. All right, so we're going to have that definition in mind. And we're going to use that to help us describe the difference between absolute convergence and conditional convergence. Right, so we've got our conditional and we've got our absolute. Now, an infinite series is absolutely convergent if two criteria occur. The first is that the general infinite series, okay, without the absolute value bar, so just the series, is convergent. So if this is true, and the sum of the absolute value of the series is convergent, then our infinite series will be something we consider absolutely convergent. And all that really means is that we've got a situation where it is more strongly convergent. Okay, so it is absolutely convergent. But what makes something not absolutely convergent, but is what we call conditionally convergent, is if our regular series, so without the absolute value, is convergent, right? So that same part holds true. But this absolute value version is divergent. Okay. So if you do one of our many tests and you find that the regular series is convergent, all you've discovered is it is at least conditionally convergent. But if you look at the absolute value one, if it's also convergent, then you've got a situation where the infinite series is absolutely convergent, and the infinite series is conditionally convergent if the absolute value one is divergent. Okay. Now, one thing to keep in mind is if a series is absolutely convergent, then it is also considered convergent. All right, so it's sort of like the more dominating one. So let's just take a look at 3 different examples where we practice determining whether an infinite series is absolutely convergent, conditionally convergent, or divergent. Okay. So let's start with example number 1. We've got this infinite series, which is the -1 to the n over n. All right. So let's take a look at just the regular series, so no absolute value or anything. What test would we use to determine whether this infinite series converges or diverges?
Alternating series test.
Yeah, we would use the alternating series test, right? So the alternating series test says that we have to have 2 conditions that are true in order to know that it's convergent. And so one is that we're looking at b sub n. So does the limit as n approaches infinity of 1 over n, which is our b sub n, does that equal 0? And I think we can take a quick look at that and say, yeah, 1 over infinity is 0, so it satisfies the first constraint. Now, the other piece we have to determine is whether or not is b sub n decreasing. And if we take a look at 1 over n, yes, it is decreasing. And so what we have here is that using the alternating series test, we have that this is convergent. Okay. So we know at this point that it's not divergent. It's either absolutely convergent or conditionally convergent. So all we've done so far is sort of check like this first one. Is the series convergent? And it is. And so now we have to say, let's take the absolute value of it and see, is that convergent or is it divergent? All right. Now, if I want to take the absolute value of -1 to the n over n, what's another way that I can rewrite that?
1 to the n over n.
Okay, we could do that. Take it one more step. How else could we write this?
One over n.
Which is
As
1
a
over n.
discontinuous function.
Yeah, we could just write this as 1 over n, right? Because 1 to the n is always going to give us 1. Okay, so now this is our absolute value definition, or really it's just the b sub n part. So b sub n by itself, does this converge or does this diverge?
Converge.
Diverge.
This one diverges, okay? So because this diverges, we can say that this infinite series is only what we consider conditionally convergent. Because the whole thing, the regular a sub n converges, but when we take the absolute value, that a sub n diverges. All right, so it's not convergent all the time, it's convergent under a very specific situation. All right. Okay, so let's kind of take that and try the process again with a very similar kind of question. So this time in example 2, we've got determine if this infinite series of -1 to the n over n squared is absolutely convergent, conditionally convergent, or divergent. Okay. So to find out whether a sub n converges or not, we need to use the alternating series test again. And so if we take the alternating series test, we've got the limit as n approaches infinity of 1 over n squared. And I think upon a quick observation, we can see that's going to go to 0. Okay. So it satisfies that first part. Now, is 1 over n squared decreasing?
Yes.
Yeah, that's a decreasing function. So we can tell from here that it does, this is convergent. Okay. Now, in order to determine absolute or conditional, now we have to say, let's just take the absolute value of it and then re-look at that series and see if that converges or if that diverges. And so using our same reasoning, the absolute value of -1 to the n over n squared, another way we can write that is the infinite series of 1 over n squared. Okay, or again, because it's an alternating series, this is our b sub n. So 1 over n squared, does that converge or diverge?
Diverge.
Converge.
This one is a p series, and that p is larger than 1. So it does converge, okay? And so because both the a sub n as well as the absolute value of a sub n converge, we have, oops, you have an absolutely convergent situation here, okay? Whereas in the first one that we took a look at, we ended up with a conditionally convergent situation, all right? Does that make sense how we can sort of determine the difference between an absolute convergence and a conditionally convergent?
Yes.
Yes. Okay. We've got one yes. Hopefully there are more yeses. Okay. So let's take a look at one last example of absolute versus conditional convergence and divergence, all right? So in this case, we've got an infinite series of sine n over n squared. And so when we're thinking about whether or not this is absolutely convergent or conditionally convergent, okay, is this an alternating series here?
Yes.
Yes.
Someone remind me, what is the definition of an alternating series?
Where the values are going from negative to positive.
Yeah, so it is when the values go from negative to positive, but we actually need to be a little bit more specific in the sense that it's like every other term is positive or negative, meaning it alternates, like it's positive, negative, positive, negative. Now, I would agree that sign n changes from positive to negative on some sort of regular cycle, but I don't know that we can say that it's alternating because sine of 1 and sine of 2 and sine of 3 could all be positive or negative depending on whether we're in degrees or radians here, but they're not necessarily flip-flopping between positive and negative like every other term, okay? So it's not quite an alternating series, but we can take a look at still looking at, is it convergent or divergent, okay? So now I wanted to choose this example because some of you on Thursday's exam had a, had a sine or cosine function in there. And so sometimes it was sine, or sometimes it was cosine, sometimes it was like sine squared or cosine squared. But what are the largest and smallest values we can have for sine?
Negative 1 to 1.
Yeah, so sine n can only go from negative 1 to 1, okay? And so what we have here is that if we wanted to think about a comparison test here, I think a comparison test would actually be quite nice, then we could say, well, we need to know if we're comparing sine n over n cubed to another function, a good function might be 1 over n cubed, okay? So if we're looking at the comparison between these two, is one always bigger or smaller than the other?
No.
No,
Why not?
because sine can be positive or negative.
Yeah, but what's the largest value sine can be?
1 is the largest, so yes, it is larger.
Yeah, sine n can only be as big as n, or it could go all the way down to negative 1. All right, so this numerator, this numerator here can only go between negative 1 and positive 1. So let me ask you that question again. Is there a relationship that we can establish between sine n over n cubed and 1 over n cubed?
No.
Less than and equal.
Which one's going to be less than?
Less than and equal.
Yeah, so the left one is going to be less than or equal to this. Because I have on the top values that can only go between negative 1 and 1. I don't have any larger numerators. The top is not getting any bigger than this numerator over here. So in that case, if the denominators are, or the numerators, I'm sorry, if the top is always smaller than the 1, then what we're going to get is, because 1 over n cubed converges and is greater than or equal to our a sub n, we know that a sub n also converges. Okay. So if 1 over n cubed converges, and we know that because it's a p series with p greater than 1, okay, and it's always larger than this original infinite series, then we know that the original series also converges, right? Now that sort of explanation I just wanted to make really clear, because as I was looking over the exams from Thursday, Some of us just wrote down converge or diverge, and we didn't really take the time to explain our thinking. And for some of us, that actually led us to make incorrect conclusions, okay? So it's really important that you know, like, with the particular test you're using, does it follow the behavior of the first of your comparing function, or is there like a number at the end and the number tells you what to do? And so that's something that I would encourage folks to maybe go back and study a little bit more if that's what you missed on the last exam. But it is important that we know, like, that we can state explicitly what is happening here, okay? Now, if we just compare A sub n to this B sub n, and then we're just saying, okay, at this point we know it's conditionally convergent. But we want to figure out if it's also if it is absolutely convergent or just conditionally convergent. And so to do that, we could repeat the process, but we could say, I'm going to take the absolute value of psi. That will make sure that we're only looking at positive values over n cubed. And we could compare it to the same function again, 1 over n cubed. Now, by putting those absolute value bars, did we change the relationship between our A sub n and our B sub n?
No.
No.
You're right. It's still going to be larger, which means that this still converges. And so since they both converge, we want to make sure that we know that means that this particular infinite series is absolutely convergent, okay? Okay, so that's kind of an introduction to absolutely convergent versus conditionally convergent. I know we didn't see any examples of divergence, but I wanted us to focus more on like clarifying the difference between absolutely and conditionally convergent. So are there any questions at this point about absolute versus conditional convergence?
I have one question on the example we just did.
Yeah, for sure. What's up?
So even though that the sign ranges from -1 to 1, in order to match the criteria for an alternating series, it has to immediately change from A sub 1 to A sub 2 to A sub 3. It has to immediately go from positive to negative to positive to negative.
Yes,
Okay.
that's correct.
So, all right, thank you.
You're welcome. Okay. So I actually think that the ratio test and the root test, which we're going to learn today, are pretty fun. So I think that you'll like them better than, again, some of maybe like the basic comparison test I think was a little bit trickier. But the ratio test, which is the first one we're going to take a look at, okay? So it says, suppose we have some series A sub n. And now keep in mind that this sigma notation is, we know we're looking at a series, and that occasionally the textbooks, the instructors, whatever, may not put a number on the bottom and a number on the top, okay? But if we're saying it's an infinite series, we're implying that the top goes to infinity, okay? So that should be something that, and I think we're all aware of that. The question though sometimes is like, what's the bottom starting number? And so that's going to be something I'm going to talk about a little bit today. Like, how do you kind of know what that bottom number is going to be? Okay. But what we're going to do is we're going to define L, capital L, to be the limit of a given ratio. And so we're going to take the ratio of A sub n plus 1 over A sub n, all right? So another way that we could think about writing this is we're going to take the limit as n approaches infinity of A sub n plus 1 times the reciprocal of A sub n. Okay, so those mean the same thing, but I think sometimes when we're plugging in our equations, it's a little bit easier to take a look at that second one where it sort of expanded into two different things, okay? So we've got our A sub n plus 1, and this one is our reciprocal of A sub n. Now, when we were looking at the limit comparison test, it did not matter which one was on top or which one was on the bottom. But for the ratio test, it is important. We need to have the a sub n plus 1 in the numerator, okay? So this a sub n plus 1 has to be in the numerator, and then the a sub n, we could think about it as being in the denominator, or that's the one that we take the reciprocal of. Okay, so that order there is gonna matter. Okay, so we're gonna find L, and it's gonna be a lot of like, the first step looks incredibly messy, and then we're gonna use a lot of like different rules, like exponent rules and things, to cancel a bunch of stuff out. And at the end, we should get some value for L, okay? So L can be a number, it can be 0, it can be positive, it can be negative, maybe. All right, let's come back to that one. It could equal 1, it could be infinity. So there's a lot of options for what L can equal. But at the end of the day, there are really 3 categories that we want to think about. If L is smaller than 1, if L is bigger than 1, or if L equals 1. And that will tell us what that series does. So if L is less than 1, we're going to have a series that is absolutely convergent. Okay, so if L is less than 1, that means absolute convergence. If L is greater than 1, that means we're going to have a divergent series. And bad news bear, if L equals 1, it might be divergent, it might be conditionally convergent, it might be absolutely convergent. So 1 is actually not a number that you hope to get out. Okay, if you get 1 out, it's kind of like inconclusive. You didn't get any information from it. Okay, so if you get L equals 1, we can kind of consider that to be inclusive. All right. So when we perform these tests, we're really hoping for a clear-cut answer, like that number L is bigger than 1 or it's less than 1. We're really not hoping for just 1. All right. But as I was kind of preparing these notes yesterday, I was like, I mean, it's nice to have a bunch of words and like, if this happens, then that happens. But I was also thinking that we could kind of take these phrases and put them on a little number line, maybe, and have 1 be sort of the middle of our number line. So if we have anything less than 1, is going to be absolutely convergent. Okay, so anything less than 1 will give us a situation where that infinite series is absolutely convergent. And I should have picked a different color, but that's okay. If we get something that is larger than 1, we're going to get a situation where that infinite series is divergent. Okay. And then sort of the number we hope we don't get is 1, because this is inconclusive. Okay. So if that little diagram is a little bit more helpful to kind of help you remember like what happens when you get what number, that could be another way to kind of, think about that content. All right. So diagram or the words, really up to you. But at the end of the day, we want to know that we have the right L value, okay? So before we jump into that, let's do a very quick review on factorials, okay? Anybody know what the symbol for a factorial is?
Exclamation mark.
Yes, exclamation mark. Okay, so when we see an exclamation mark in math, doesn't necessarily mean that we're like super excited about that particular number. It means that we're going to have a factorial happening. Okay, so let's take a look at a few values. What is 1 factorial?
Oh, 1 times 0.
1.
Ah, which one is it? Is it 1 times 0 or 1?
1.
It's 1.
It is 1. Okay. What about 2 factorial?
2.
How'd you get that?
1 times 2.
I'm going to ask you to say that the other way. 2 times 1. Okay. And you're right, that does go to 2. All right. What about 3 factorial?
6.
6.
Okay, because we do 3 times 2 times 1, which is 6. Okay. We could also write 3 factorial as 3 times 2 factorial. Yeah. How would we write 4 factorial?
4 times 3 factorial.
And so we could get 12. What's another way we could write 4 factorial?
4 times 3 factorial.
Times 3 factorial, yeah, okay. Now 5 factorial would be 5 times 4 times 3 times 2 times 1. Kind of get a little bit less excited every time, right? You just sort of lose 1. And then maybe another way we could write this is 5 times 4 factorial, right? How else could we write this in terms of factorials?
6 factorial minus
20 times 3 factorial.
We could do 5 times 4 times 3 factorial, yeah. How else could we write this?
five times 4 times 3 times 2 factorial.
Yeah. Okay. And we can always just calculate it out, right? So we get, what do we get? 20 times 6, 120, right? Okay, so in general, like we can see factorials, but when you see factorials again, it'll be in discrete math if you have to take discrete. You kind of do a lot of work with factorials. I think it's pretty cool. But it's almost less important to know the exact number and more important to know the pattern and different ways that you can write it, okay? So if you're like, I know 3 factorial 6, that's awesome. But it's maybe even more beneficial to know that 3 factorial is 3 times 2 times 1. Or we could write it as 3 times 2 factorial, okay? So in general, if we have n factorial, all right, we know that that's going to be n times n minus 1 times n minus 2 times, and you keep going, okay? Now, when you are using it in the context of maybe simplifying things, it's actually quite nice to write n factorial as n times n minus 1 factorial, okay? And that is really just what we said when we did 5 times 4 factorial, or that 4 factorial is 4 times 3 factorial, or 3 factorial is 3 times 2 factorial, okay? And so if we were to go all the way back to 2 factorial, we could write this as 2 times 1 factorial, right? 2 times 1 gives us 2. Now, using that, how can we write 1 factorial?
1 times 1 factorial.
1 times, not 1,
0 factorial.
Yeah, why'd you get 0 factorial?
I plug in 1 inside, and minus to 1, and then
Yeah.
times factorial.
Yeah, because we have n, and then we took out this n minus 1 factorial, right? So if we follow that pattern, you're right, we have 1 times 0 factorial. Now, we knew from the beginning that 1 factorial was 1, right? So that means that no matter how we write 1 factorial, we should get 1. So what's the only way that I can define 0 factorial so that all the other factorials work out?
Equals 1.
Yeah, it can't be 0, right? Because if it was 0, then 1 factorial would be 0. 2 factorial would be 0. So 0 factorial is actually defined to be 1. Okay. Kind of an interesting tidbit, I think. Sometimes we start all our factorials at like 1, 2, 3, and we kind of don't really stop to think about what 0 factorial is, but there are moments in your later math where you might need to know that 0 factorial equals 1. Okay. But all of this is to say, today we're going to be looking at some things with factorials, and it's going to be useful if we could maybe break things down into like n times n minus 1 factorial, okay? Now, one last note on factorials. Can someone explain to me the difference between 2n factorial versus 2 times n factorial?
The distributive property.
The factorial is inside the parentheses and the one's outside, so it does make a big difference.
Does it change your answer or not?
Yes.
Okay, how does it change your answer?
With your 2n factorial, you're going to go from 2n to 2n minus 1, 2n minus 2, all the way down to 1. And then with the 2, that 2 is going to be distributed to your n times n minus 1 times n minus 2, all the way down to 1. And so whatever you get out of that, that answer is multiplied by 2.
Okay. Okay. So when you say something like distributive property, you need to be a little bit more specific about that, right? Like, what do you mean by distributive property? Does that mean that you can just distribute the 2n later? Does it mean that you can't? So based off of this, are we going to get the same answer or not?
No.
Okay, tell me at what point you start getting a different answer.
2.
Well, it looks like the one on the right might turn into a negative, and the one on the left is like stays a positive because it's greater. The 2n is greater, but on the
Right after the n term?
Yeah, so this 2n, right, that's the first part. That would be the same as if I did 2 times n. So like, if you only look at the first term, it might look totally the same. But as soon as you start to go a little bit further from that, exactly, right? Carl is saying that at the n minus 1 factor, when you distribute the 2, right, we would get 2 times n minus 1, which is really 2n minus 2. And that is not the same as the second term from the 2n in parentheses factorial, okay? So with factorials, because the factorial is like something done to the number, whether we have the 2 in the parentheses or out of the parentheses actually does make a difference, okay? So I just want us to kind of keep that in mind as we go through these questions, that where we have our parentheses definitely matters. So the way we write our parentheses, we really want to be super careful about that, okay? Okay, so I actually think we're gonna take our break here. So it is 10:17. We're gonna come back at 10:27. So we'll take a 10-minute break. And then we'll take a look at the ratio test as well as the root test, okay? So I'll see you folks back here in 10 minutes. All right, folks. So we're going to hop back into our 11.5. We spent a lot of time kind of setting the foundation of what we're going to be doing, and now we're actually going to get to the ratio test and the root test, okay? All right, so we talked about absolute versus conditionally convergent, just to kind of set the stage for like why we need these other tests. And then we talked about the ratio test, okay? So the ratio test, we have to have our a sub n plus 1, and we're going to take that and we're going to multiply it by the reciprocal of a sub n. Now, we're going to be taking the absolute value here, and that's going to be really important, okay? So we are going to be taking an absolute value. We're going to be finding a limit, and then at the end of the day, we want to classify our answer for L as less than 1, greater than 1, or equal to 1. Again, equal to 1 is kind of like our worst case scenario because it doesn't really tell us anything. But if it's less than 1, we have an absolutely convergent case. If we have L is greater than 1, we've got a divergent case, okay? So let's take all of that right now, and along with what we just talked about with factorials, and let's apply that to example number 4. Okay, so we see the factorial. Pretty much anytime I see a factorial, I'm like, ratio test, okay? So when I see the factorial, I'm thinking ratio test. That is one of the nice things about the ratio test. I think it's a little bit more clear when you should use the ratio test, okay? All right, so we see the factorial. Let's set up our L expression. So we know that L is going to equal the limit as n approaches infinity of a sub n plus 1 times the reciprocal of a sub n. So if I want a sub n plus 1, what do I replace n factorial with?
N plus 1.
Yeah, I'm going to replace it with n plus 1 factorial. Okay. Now, if I see 5 to the n on the denominator, how do I make that an a sub n plus 1?
5 to the n plus 1.
5 to the n plus 1. Good. Okay. So times, what colors did I use here? Yellow and blue. Okay. So this is our a sub n plus 1. Okay. Now we have to multiply it by the reciprocal of a sub n. So we're going to multiply it by 5 to the n over n factorial. So this is 1 over a sub n. Okay. Now let's find our limit as n approaches infinity. But let's simplify first, okay? So what is another way that I can write n plus 1 factorial?
N log 1 times n factorial.
Beautiful. N plus 1 times n factorial, right? We just talked about that right here. So this n is like our n plus 1, because that's what we're taking a factorial of. And then when we lose 1 from that, we get the n factorial part, okay? Now I'm going to combine everything into one fraction while I'm here. So I'm going to have my 5 to the n on the top. And on the bottom, what is another way that I can write 5 to the n plus 1?
5 times 5 to the n power.
Okay, so we could write it as 5 to the n times 5 to the 1, right? Because we're adding the exponent, so we can multiply like the base to the first exponent times the base to the second exponent, okay? And then we still have that n factorial from the 1 over a sub n. So I've sort of expanded this a little bit. So this step is really important because what it allows us to do is start to see where we can reduce things, right? So right away, I'm like, ooh, that 5 to the n and that 5 to the n, that reduces to 1. Excellent. I don't have to worry about that, okay? What else reduces?
Factorial.
Exactly, the n factorial and that n factorial, those reduce as well. Okay, so what do we really have left here then? We have the limit as n approaches infinity of the absolute value of n plus 1 over 5. Okay, so the beginning is kind of intimidating, and then the next step sometimes gets a little worse, but then from there, a lot of things cancel. And now we're saying, let's find the limit of a relatively simple expression, n plus 1 over 5, okay? Now, we know that if we plug in n values, that the smallest it can ever be is 0, and that the largest it can ever be is infinity, right? So if we go back to the original problem here, I know there's an implied infinity on the top, and a lot of times the bottom number is dependent on our expression. So if I think about any restrictions for n, there are no restrictions. So this bottom part is really n starting at 0, okay? So if I plug in numbers like 0, 1, 2, 3, is my expression in the absolute value ever going to be negative?
No.
No. So what we can do at this point is we can actually drop the absolute value bars because we know we're already going to get a positive, okay? So it's not like we drop them like, ooh, I don't know what to do with them, let me just not write them. It's like, oh, I've made an educated decision that whatever I get inside that is already going to be positive, so I don't need to write it again. And what that allows us to do is now we can kind of plug in infinity. And we can see very quickly that that's going to give us infinity, right? The power on the top is overpowering the 5 on the bottom. And now we have infinity, okay? What does this mean? Because infinity in all of the tests that we've seen kind of mean a different thing every time. So
Diversion.
how do you know? What tells you that it's diverging?
Equal 1.
Infinity is greater than 1.
Yeah, we need to compare our L to 1, right? That's what we're comparing it to. So when you're explaining your reasoning to me, you need to bring it back to this point. You need to be very specific. Like you can't just say, oh, it goes to infinity, so it diverges. You need to say, okay, L is infinity, which is greater than 1, which means this series diverges, okay? So we can go back here. We can say infinity is greater than 1. So this series diverges. Okay. So that's a case of how we use our ratio test and then how we interpret our results, all right? Are there any questions about example number 4?
I have one question.
For sure. What's up?
If you did, you know what? I'm gonna save it till we go through all the examples. Never mind.
Okay. All right. So let's take a look at example number 5 here then. Okay. I mean, you can kind of see on the bottom that example 6 has a factorial. So again, that factorial means, oh, we're going to use the ratio test. But if you look at example number 5, you'll notice there is no factorial. Okay. But here are a few indicators. If you see some powers, so you see a power of n, but then this one is 2n plus 1. Sometimes when you have powers, that's a good time to use the ratio test, okay? But sometimes that also means it's a good time to use the root test, which is the second test we're going to learn, all right? So let's just go through this one as if we were doing the ratio test. And when we get to the root test, I think we'll maybe see why this one is not a great candidate for the root test. But if we're using the ratio test, again, what we want to do is find a value for L. Because if L is greater than 1, we know it diverges. If L is less than 1, we know it absolutely converges. And if it equals 1, that is inconclusive. Okay. So let's plug in for our n plus 1, our a sub n plus 1. That's going to turn my negative 10 to the n into negative 10 to the n plus 1. How do I write 4 to the 2n plus 1 for an n plus 1 term?
4 to the 2n plus 1 plus 1.
Like this?
Yes.
Okay. That is not correct. And I'm actually so glad that you said that, because we can't just plug in like a plus 1 at the end and be like, oh, I hope that takes care of it.
What were the parentheses?
Where?
Between the n and the 1 next to the 2.
So here?
Yeah, so you could like multiply or distribute afterwards.
Where do I close it?
The first, after the first one.
Good. Okay. Now it's correct. All right. So if you are on an exam, please make sure that your parentheses are super, super clear for what you're doing, because this is absolutely correct. You've got your n plus 1 everywhere you saw an n before, whereas the version without the parentheses actually is not correct. All right. Now, the last part, this n plus 1, I think that's a little bit easier because we have n plus 1, and then we still have our plus 1. Okay? So all of this here is our a sub n plus 1. And to that, we have to multiply the reciprocal of reciprocal of a n, which is going to give us 4 to the 2n plus 1 times n plus 1 over negative 10 to the n. So this is our 1 over a sub n. Okay. All right. So remember, this first step is kind of like, okay, we're just plugging in everything. And the second step, where we might need to expand a few things, is really where it's going to get messier before it gets a lot better. Okay. So let's put everything over one fraction. I can write negative 10 to the n plus 1 as negative 10 to the n times negative 10 to the 1. Okay. Times, oops, four to the 2n times 4 to the 1, right? So I'm using that same exponent rule to split that. And then I'm just going to keep my n plus 1 at the end. Right? Are there any questions about how I've simplified the numerator so far? Okay. So with the denominator, I'm going to end up with 4 to the 2n times 4 to the 2 times 4 to the 1. So I'm expanding all those exponents. In parentheses, I'm going to have not n plus 1 plus 1, but n plus 2. And then I have a negative 10 to the n. Now, this is sort of the messy step, but things should get a lot better at this point. Those reduce. These reduce. This reduces. Okay. So let's see what that gives us. We're still going to be taking the limit as n approaches infinity. On the top, we have a negative 10 times n plus 1. On the bottom, we have 16 times n plus 2. Now, I notice that the negative 10 is negative, and this 10 and the 16 are constants. So the absolute value of negative 10/16 is positive 10/16, and I can pull those out to the front, which is nice because now I know n plus 1 is always positive. I know that n plus 2 is always positive, so I don't have a need for my absolute value bars anymore. What is this going to approach?
1.
It's going to approach 1. How do we know that without having to use L'Hopital's?
Because n over n makes 1.
Yeah. Maybe more specifically, the 1n over 1n, right? We're just the coefficients that we're dividing here. So we get a ratio of 1. So we get 5/8 at the end for our L value. So 5/8, how does that compare to 1? Bigger?
Less.
It's less than, so it's convergent, absolute convergent.
Exactly. Okay, so at the end, we need to say 5/8 is less than 1. So our infinite series is absolutely convergent. Okay. All right. Let's try number 6. Okay. So number 6, I see the factorial and I'm like, yes, factorial, that is a good time to use the ratio test. Okay. I don't want to worry about integrals. I don't want to worry about finding something to compare it to. I just want to say, what's the ratio between a sub n plus 1 and a sub n? So let's set this up. The limit as n approaches infinity. Absolute value, I'm going to get n plus 1 squared, right? We really want to make sure we have our parentheses there, over 2 times n plus 1 minus 1 factorial times the reciprocal, so 2n minus 1 factorial over n squared. Okay, so we're going to keep this n plus 1 squared, all right? I know sometimes we're like, ooh, I know how to FOIL, and that might feel like the only thing you know how to do in a problem. Usually, though, at this stage, it's just not worth foiling out, okay? So times my 2n minus 1 factorial. So there's not a lot I really need to clean up on the numerator, but I think the denominator is where we might need to reframe this, right? So if I distribute that 2, I'll get 2n plus 2 minus 1, or I'll get 2n plus 1, right? So down here, I really have 2n plus 1 factorial times n squared. Now, in looking at this, there's really not a lot that I can cancel at this point. So it might be useful for us to think about how we can rewrite this 2n plus 1 factorial so that we can get rid of some stuff. So what might be a way to rewrite just that one piece in the yellow?
Two n plus 1 times n times 2n minus 1 factorial.
2n plus 1, I buy that part. What was that second part you said?
Times 2n.
Times 2n, yes, okay, I didn't hear that 2 at first. Exactly. So 2n, because that's 1 less than 2n plus 1, times 2n minus 1 factorial. And then I have my n squared. And so what we've done is expand our 2n plus 1 factorial into something like this. And in this case, we actually had to take out the first two terms. So it's kind of like if we wrote 5 factorial as 5 times 4 times 3 factorial, okay? So sometimes you have to sort of unpack more than one term, but our end goal is always to get it so that things reduce, okay? So clever, I like that. All right, so let's see what we have on the top here. I think at this point we can actually drop the absolute value bars because n plus 1 squared on the top, that's just going to be a positive number. So I don't need to emphasize again that it's going to be positive. And on the bottom, I have 2n plus 1 times 2n times n squared. Now, I know in this case that not everything simplified as much as it had in the past, but what does this value approach when we're getting n towards infinity?
0.
I want to say 1.
Mariah, tell me how you know the 0.
I just see that the denominator goes, if you plug in infinity, it goes to 0.
The denominator goes to 0?
It goes to infinity, and then that's why I made it a 0.
Okay, but tell me why it didn't go to like 1.
Yeah, 1, I believe. If you see on the top it's squared and the bottom is squared on the n, and then the top is greater than by 1, so I believe it might get closer to 1 because the numerator is greater than the denominator.
All right, well, let's unpack this a little bit more. For any n value that I plug in, I'm going to have something, some value, and I'm going to be squaring it, like I'm raising it to the second power. Yeah. If I were to plug in a number for n on the bottom, I'm really getting something to what power?
It would be the 4th.
To the 4th power, right? Because I've got a 1, and 2. So 1 plus 1 plus 2 gives us 4, all right? So it does, as Kevin said in the chat, that it goes to infinity over infinity, right? Because infinity squared is going to be infinity, infinity to the 4th is infinity. But we can actually also say that because the power on the top is smaller than the power on the bottom, right? We are overpowering the numerator, that it is going to be getting towards 0, like Mariah had said. Okay. You can also use L'Hopital. You'll end up with a number on the top, and then you'll still have infinities on the bottom, and so that will give you a 0 if you use L'Hopital. Okay. But the 0 in itself as a number could mean a lot of different things depending on which test you're using. And so we want to be really clear here that 0 is less than 1. So our infinite series is absolutely convergent. Okay. Now, let's go back to the sigma notation here. We know on the top that we have infinity. Okay, we know on the top we have infinity because we're looking at infinite series. Could I have n equals 0 on the bottom?
Yes.
I was gonna say no.
Okay, tell me why yes and tell me why no.
I thought yes, because when you plug in 0, never mind.
Okay, tell me why no, Mariah.
N squared.
Just because having a 0 in the denominator, just can't do that.
I won't have a 0 in the denominator though. Like 2 times 0 is 0, but then I have to minus 1.
You can't have a negative factorial?
Yeah, so we can't start at 0 because that would give us a negative factorial, okay? Can we start at 1?
No.
Yes. We'll get a 1 factorial on the.
Okay, and it's okay on the top, right? We could have a 1 on the top.
Yes.
So for that sort of reasoning, we wouldn't want to start at 0 for this particular series. We would want to start at 1, okay? So I know that's kind of like, how am I supposed to know that? And that's why I want to make this a little bit clear. Like, in a lot of these cases, if there's not an index on the bottom, we kind of have to use, I don't want to say common sense, that's a terrible phrase to use here, but we want to think about what makes sense for that particular series, and it might be different. So like sometimes you may not be able to have a 0 on the bottom. Sometimes you may not be able to start at 1. Sometimes you have to start at 2 or 3, okay? Okay, so any questions so far on the ratio test?
Yes, I have one.
Okay, what's up?
So if you come to a problem where you have to use the ratio test and you come out with a 1 and you have factorials in your original problem, what do you think would be a next good test to go to when you're having to deal with those factorials?
I think it would really depend on the given situation. I don't think we're going to see any of those, but it's just something to kind of be aware of.
Okay.
Okay. Okay. So let's take a look at these last 2 examples for the ratio tests, okay? So let me give you a moment to kind of start to set these up. You know that we're using the ratio test, so let's plug numbers in, see what we get, and see how we can interpret our results, okay? What does the number at the end, like what are we comparing it to? What does it mean? Okay, so for example number 7 here, we should get a case where we just plug in our n+1, and hopefully we've made it clear by this point, like how we plug in that n+1 and how not to. But when we sort of expand what we have into our different, using our different exponent rules, we'll start to see that a lot of the things cancel out. So this 9 to the n and that 9 to the n, these two and these two. And so we really don't have a ton of terms left for example number 7. In fact, I think our numerator boils down to 9n. And what does our denominator boil down to?
Two times n plus 1.
2 times n+1?
Yeah, 2 times n plus 1.
Yeah, I would say that's incorrect. Yeah, Kevin, it's going to be -2 times n+1. Okay.
But then the absolute will make it a positive.
Right, but we still have our absolute value bars at this point.
Oh.
So if you just lose the minus sign here, that's not correct.
Oh.
Okay. But in the next step, you are correct, right? We're going to take that 9/2. We're going to pull it out to the front because those are the constants. Once we remove them from our absolute value bars, we know that they have to be positive. And then the rest of it stays because there's no way that n over n+1 is going to be negative. Okay. Now, this limit is going to go to what?
1.
Yeah, this is going to go to 1. Okay. And so we're going to end up with 9/2 as our L value. Okay. We're going to take 9/2. What do we compare it to?
It's greater than 1.
So that means,
Diverges.
yeah, that means that we're going to get a divergent series. Okay. Now, I wanted to use this example right here because if you forget the absolute value bars, what value do you end up with for L?
-9/2.
-9/2, right? You forget the absolute value bars, you get -9/2. You're like, -9/2 is less than 1, so it's going to converge. That would give you the incorrect answer, right? So like in this case, having the bars, the absolute value bars, does actually make a difference between a correct answer and an incorrect answer, okay? So just make sure that you have those absolute value bars, that you take care of any constants that you need to, but that you don't forget to drop any of those negative signs at the appropriate time, okay? All right. Let's take a look at this one last example here. We've got example number 8. I think this is maybe the simplest looking one that we've seen so far. And on the top, we'll get n+3. On the bottom, we'll get 2 times n+1 plus 7. We're going to multiply that by 2n plus 7 over n plus 2. Now, if I wanted to simplify this a little bit more, I get n+3 times 2n plus 7 over 2n plus 9 times n plus 2. And nothing really cancels, right? What does that limit go to?
1.
How do you know that?
When you multiply on the top the n times the 2n, you're going to get 2n squared, and same thing on the bottom. So you will have a ratio of 2n squared over 2n squared. So the coefficients will go to 1.
Yeah, exactly. Now this again is sort of like what we don't want to get out of here. Like if we do the ratio test and we get a 1, that means that it's inconclusive. Okay. Now here's the deal. Anytime you see polynomials like this, okay, where you have, you know, n plus 2 on the top and or something like that on the top and something similar on the bottom, you've got your rational expression with a polynomial on the top and a polynomial on the bottom, the ratio test is going to be inconclusive. All right. What might have been a better test to try for example number 8?
Limit compare.
I think this is one where if you can, see that right off the bat, you know that if you apply the divergence test, you're going to end up with a 1/2 as your a sub n, like as n approaches infinity. So this series does actually diverge. Okay. So even though the ratio test said it was inconclusive, if you use another test, you'll find out that it diverges. Okay. But this is a good example where we don't want to, just because we see a fraction line, use the ratio test, okay? So let's move on to the root test, okay? So the root test operates kind of like some of the questions look similar. And so I want to talk about like how you know when to use which one, all right? So the root test says something like this. Let's suppose that we have this infinite series and we're defining L. So we're going to use that same letter L again, but this time we would define it differently. L is going to be the root, the nth root of a sub n. So we're not going to do like an a sub n plus 1 to an a sub n. In fact, we're just going to take the nth root of whatever we have, okay? Now, our interpretations at the end are going to be very similar. So whatever value we get for n, if L is less than 1, is going to be absolutely convergent. If L is greater than 1, the series is divergent. And if L is 1, you've still got your inconclusive. Okay, so our interpretations do not change for the ratio test and the root test, but the way we set it up does. So one thing that I want us to sort of have in our back pocket before we approach some of these problems is this concept. So if I take the limit as n approaches infinity of n to the 1 over n power, okay? Now we've seen this before in this course. If we just plug in infinity, we'll get infinity to the 0. When we see infinity to the 0, what does that equal?
Indeterminate form.
Yeah, this, my dears, is an indeterminate form. Okay. So I've seen a few people who are still saying, oh, infinity to 0, anything to the 0 power is 1. And that's not quite correct. Okay. So it's important that you recognize that it is an indeterminate form. Now, just in sort of preparation for the final, how do we approach a situation where you have the infinity to the 0?
We use
Transform it to y equals, and then the next step is the limit of both sides.
The limit of both sides. But how do we get rid of the indeterminate form?
Natural log.
Yeah, we're going to have to use the natural log, okay? So as it turns out, when you do all of the natural log stuff, okay, what we're going to end up getting is we will end up getting 1. That's why 1 has been a very common answer for us, okay, in a lot of these questions about indeterminate forms. But that doesn't mean that we can jump right to that conclusion every single time we see the infinity to the 0, okay? Because we might have some other coefficient somewhere that might give us a different answer, like e to the 4th or e to the 3rd. We've seen that as well, okay? But in this particular context, we're looking at saying that if we take the limit as n approaches infinity of n to the 1 over n, we're going to define that as being equal to 0. Okay. Again, this is specifically for our root test here. But let's see how that might be helpful. Okay. So for example number 9, let's see what we have. I see n to the n, so I see a power of n, and I also see the denominator has powers of n. So when I see powers of n and no factorials, that is a good time to use the root test. Okay, so they look really similar, but if they don't have the factorials, they only have the powers of n, that's a really good indicator that you should use the root test. Okay. So let's set up our L. L is going to be equal to the limit as n approaches infinity of, I don't want to do an n plus 1 because I'm not doing the ratio test, but instead I'm going to take the absolute value of my series and I'm going to raise it to the power of 1 over n. Okay. All right. Now, if we're raising things to a power, we take that power, we distribute it to that power, and we also have to distribute it to the power on the bottom. And so when we do that, we're going to get n to the n times 1 over n, because when we raise a power to a power, we have to multiply. And on the bottom, we're going to get 3 to the 1 plus 2n times 1 over n. Okay. Now let's see what starts to go away. N times 1 over n. What does that go to?
1.
1. Good. So in my numerator, I have n to the 1 power. If I distribute similarly in the denominator, I'm going to get 3 to the 1 over n plus 2. Now, I know that n can't be negative because by definition, a series has to start with the 0 or the 1 or anything that gets me a positive value. Okay. I know that similarly, 3 to any power is not going to be negative. So I don't need the absolute value because both parts inside are already positive. That's going to give me n on the top and 3 over 1 over n, and we could say times 3 squared. And now we can plug in our infinity. So we get infinity over 3 to the 1 over infinity times 9. So what is that going to give us?
9. I mean, infinity over 9, which is infinity.
Okay, so infinity over 9. Good, because this goes to 1. And that goes to infinity. Okay. Now let's think about what infinity means in the context of this problem. The root test says that we want to take our L value, compare it to 1. If it's bigger than 1, we know that it diverges. Okay. So we know that this particular infinite series diverges because we get a value that's larger than 1, okay? It doesn't have to be infinity, it could be a number as well, but in this case it happens to be infinity. All right, any questions on number 9 here?
Even though it wouldn't change the solution, wouldn't 3 to the 0 power be 3 times 9?
3 to the 0 power is 1.
Anything to the 0 power is 1.
Oh, yeah, never mind. Got it.
All right, so let's take a look at these last 2 examples, okay? If I sort of sneak both of them on the same screen, I can see right away from example number 10, 2 indicators that I should use the root test and not the ratio test. What is one of those indicators?
No factorial.
No factorial, okay. So what else?
The power of n.
Power of n, okay. There's actually one more indicator in here that would say, maybe don't use that ratio test. What is it?
The top and the bottom have the same power rule inside.
They're both polynomials, right? I have a polynomial over a polynomial. So in this case, that is the case where if I use the ratio test, I might end up with a 1, which is inconclusive, and then ultimately a waste of our time, right? Okay, so we know, let's not use the ratio, let's use the root. All right, so we're going to take 5n minus 3n cubed over 7n cubed plus 2 to the n, and we're going to raise that to the 1 over n power. Now this one turns out a lot nicer than the other one, because immediately we have these 2 are going to go to 1, so I just have 5n minus 3n cubed over 7n cubed plus 2. How come I didn't just lose my absolute value bars at this point?
Because we have a negative 3n cubed on
that negative 3n cubed, right? So that's why you just have to be super careful about this. But if I plug in infinity now into the absolute value, I'm going to get a negative 3 over 7, because I'm just comparing this coefficient to this one. However, we want our L value to not be negative 3/7, but L is in fact equal to 3/7. Okay. Now, ultimately, we're comparing it to 1. So in this case, it would not have changed your answer, like your conclusion, if you accidentally wrote a negative 3/7. But if we think back to example number 7, I think it was, it did actually make a difference, okay? So sometimes it doesn't make a difference, but sometimes it does actually give you an entirely different interpretation of your answer. We know that our L value is less than 1, which means that we've got an absolutely convergent series. Okay. Any questions about number 10? All right, let's try this one last question here, number 11, okay? So we could, in this case, use the root test, because I see the power of n, right? That's a good indicator that I could use the root test. But what other tests could I use for this?
the alternating test and
Yeah, we could definitely use the alternating test, right? Because it's not like the sign question we saw earlier where it was like negative for a whole bunch of values and then it became positive for a whole bunch of values. This one does, as was very nicely summarized earlier, alternate. Like a sub 1 is going to be negative. A sub 2 will be positive. A sub 3 will be negative. A sub 4 will be positive. Okay. So we could also use the alternating series test here. You're welcome to confirm your answer later with the alternating series test, but let's use the root test here just to kind of give us one more example of the root test, okay? So absolute value, negative 12 to the n over n to the 1 over n power. That's going to give us negative 12 over n to the 1 over n power. Now, if I want to get rid of my absolute value bars, there's only one term I need to change, and that's the 12. So 12 over n to the 1 over n. Okay. So in this case, we can actually use that definition we had seen earlier, this one right here, where when we see that limit as n of n to the 1 over n, as n approaches infinity, that we can assume that that's going to be 1, okay? And we could confirm that using our indeterminate form process, but in this context, it's okay to just say it goes to 1. So what that gives us then is 12 over 1, which is 12. 12 is greater than 1, so our series diverges. Okay. Now again, if we forgot those absolute value bars and we got a negative 12 instead of a 12, that would change our interpretation. We would say, oh, that actually converges, it doesn't diverge. Okay.
So for the final, are you gonna want us to show like our indeterminate form process, or is it okay to just put like we assume, you know, make sure, or we have to show the whole process?
In this context, it's fine to assume, but in an indeterminate form question, you would need to show me the work. Okay. All right, so folks, that is the root test and the ratio test. Again, I think there may be a little bit more straightforward than some of the other tests that we've learned. And the nice thing is that they sort of have the same interpretation, right? So like it all depends on what your number for L is. If it's less than 1, we've got absolute convergence. If it's greater than 1, it's divergent. And if L equals 1, it's like we should have picked a different test, okay? But that's it for today, okay? And I think that should take you through questions 1 through 8 on quiz number 14 should all be on the ratio and the root test, okay? So knowing that we kind of have a very heavy week with a final and a lot of quizzes, it's probably a good idea to knock out those 8 questions today if you can for quiz number 14. That way tomorrow you can focus on the last few questions for quiz number 14, okay? So we're gonna stop our lesson there.